I'll be looking at the interactions between the biosphere and the climate and the oceans. We'll be looking at biosphere degradation, biosphere feedbacks, the carbon sinks of the biosphere. I'll be showing up-to-date data sets. So the state of the biosphere in the global climate emergency. This makes responding to the climate emergency a great deal more urgent than it already is. The biosphere, of course, is all of life, but importantly here, it includes dead and decaying life, and in the world of nature. The biosphere runs the carbon cycle, which runs the climate. Biosphere is actually an interacting component. It's a component of the climate system. In the global climate emergency, the state of the biosphere is crucial for stabilizing global climate and the oceans. Recommended paper here, published last year, and a quote: the rapid anthropogenic climate change currently is intimately entwined with the health and functioning of the biosphere. The take-home message for all of my climate emergency presentations is that 1.5 degrees C in this case has globally severe impacts on the biosphere, and above 2 degrees C triggers multiple interreinforcing impacts on and from the biosphere. This is a big message delivered by the chair of the IPCC, Hosung Lee, at the opening of COP26, in which he stated that global warming of 1.5 degrees C and 2 degrees C will be exceeded this century without immediate, rapid reductions in greenhouse gas emissions, carbon dioxide, and methane. Global heating and climate change causes, or rather increases, multiple degradations of the biosphere. One effect of global surface heating on the biosphere is amplifying carbon feedbacks. They're called positive feedbacks. And they cause more heating and climate and ocean disruption. And this is the top catastrophic risk of global climate change. Climate change and the biosphere interact. The biosphere decline and the climate change are negatively inter-reinforcing. The biosphere, as we all know, is being subjected to a long-term accelerating trend of degradation and decline. Global climate change is impacting the whole biosphere, as well recorded by the IPCC, and this increases this declining trend, pre-existing declining trend. Many of the biosphere degradations feed back on the climate and the ocean. Here's an illustration of what we're looking at, and it ends up with a land, biosphere, climate, oceans feedback loop. We have a degraded biosphere getting worse. Then we have fossil fuels, CO2 pollution, more atmospheric CO2 being emitted. Then we have CO2 feedback from the degraded biosphere, even more CO2, and CO2 goes into the oceans as ocean acidification. Also, and particularly for this presentation, we also end up, due to the biosphere degradation, weakening of the land carbon sink. Even more CO2 being left up into the atmosphere, even more ocean acidification. Here's the headline from the big 2019 IPBES, the Ecosystem Report. Nature's dangerous decline is unprecedented. Species extinction rates are accelerating. This shows the accelerating decline of the land biosphere. This is from the World Wildlife Fund, their Living Planet report. This is their habitat index, and it indicates land ecosystems declining fast. This is from that IPBES report. the accelerating extinction. We're in the sixth extinction event. And this is an indicator of declining biosphere integrity. So it has two images from 1500. I've inverted that to show that this is a declining situation on an accelerating rate, and the more recent ones that we're more familiar with. This is my illustration of all the biosphere feedbacks, and it shows widespread climate change effects on the biosphere, many biosphere feedbacks, which are large sources. And potentially this diminishes the crucial carbon sinks of the biosphere, land and oceans. On the land, we're going to be looking at where most of the carbon is. Most of the carbon is in the higher latitudes in the Arctic. So we're going to be looking at wetland peat, very high in carbon, permafrost, frozen until recently, and the boreal forest. And this is a most recent global soil organic carbon map. I've put all these together so you can reference them. These are the many biosphere responses to atmospheric greenhouse gas emission. Global emissions are still increasing as fast as ever, and the trend in global emissions is far worse than expected. And it's not going to get better fast because of the failure of the COP26, the Glasgow COP26, recently this year. And this Glasgow COP26 shows that governments have no intention of even cutting back on fossil fuels. And the science, of course, says that they have to be stopped to stabilize climate and stabilize the oceans, ocean acidification. CO2 is responsible for about 65% of the global heating, and it's responsible for 100% of ocean acidification. And so we come to the climate and biosphere data sets. This is an illustration. This is affectionately called the BAMS. It comes out every year. This is the American Meteorological Society Climate Change Bulletin, and you can see it shows many adverse trends. This is from Working Group 1, and it shows the abrupt increase in global temperature, surface temperature, and atmospheric greenhouse gases over the past 2,000 years. From Working Group 1, at the top, you see the temperature, and underneath CO2, methane, and nitrous oxide. These are the recent data sets from the Working Group 1. Clearly, it shows they're accelerating. See the growth rate there. In the case of methane, the very rapid and huge concern in the accelerating increase since 2006. Working Group 1 has this image, this record going back 800,000 years from the ice core, and again, the more recent ones that we've seen. This is atmospheric CO2, back 800,000 years, and the CO2 limit over this time is 300 parts per million of air. It is today almost 40% higher than that 300 ppm limit. It's almost 50% higher than the pre-industrial level. There is an enormous amount of CO2 up in the atmosphere. It lasts practically forever, and we cannot afford more CO2 from feedbacks or carbon sink failure. Another one from Working Group 1 showing that atmospheric CO2 is the highest, as they say, in at least 2 million years. The rate of atmospheric CO2 increase is 100 times faster than past natural and glacial increases of warming. And it's unprecedented in records going back 40 million years. That's the rate of atmospheric CO2 increase from WMO in 2017. This is a very good double data set. It's from the Oxford University Global Warming Index. And so it's last year's global warming. The index conveniently just gives us the global warming from our emissions. And in the green underneath, the cumulative CO2 emissions. They're both accelerating clearly. And note how the global warming is even accelerating over the past decade. We have a paper published last year, which was entitled RCP 8.5, that's the worst case scenario, tracks cumulative CO2 emissions. So we're on the worst case scenario. I do this every few years. Yeah, it's a whole lot of graphs and data sets. This one shows the current data sets for the climate system and the biosphere. And the point is just to show that they are all increasing extremely fast, and you can see the acceleration on them. The bottom one in black is the emissions of greenhouse gases, the CO2 equivalent emissions. And you can see how fast that is increasing. Global warming dries and heats the forests, and that's in opposition to the CO2 fertilization forest greening. Well, warming, of course, drives heat waves, drought, forest fires, which the IPCC Working Group 1 said was now attributable to global climate change and would continue to increase these extreme weather events. Now, if these are extensive and intense, they can feed back on carbon, especially if they're combined in any ways. This is from the IPCC's fifth assessment, 2014. It shows the world's forests, and it shows the tree mortality under climate change. The quote is tree mortality and climate change, extensive tree mortality and widespread forest dieback, that's high mortality rates at the regional scale, linked to drought and temperature stress, have been documented recently on all vegetated continents. This was a most important finding of the AR5. Working Group 1 shows that global warming is accelerating. It accelerated after the 1970s. You see the huge difference between the pre-1970 map of global surface warming on the left and the other one since 1981. You'll see, as is well known, that the northern hemisphere is warming much faster than the southern. And you'll see that the subarctic and Arctic is warming the fastest of all. That matters because of biosphere feedbacks, peatlands, permafrost, and boreal forest. This shows land warming. On the left is NASA GIS, last year's land warming only, and that reached 1.6 degrees C. On the right is Working Group 1, showing that the land surface temperature increase is much faster than the sea surface. And that particularly started, you'll note, in about 1980. And you'll note that since then, the divergence between the land and the oceans has been increasing rapidly. On the NASA map, you'll see the faster warming of land, particularly in Europe and Asia, and the maximum warming, the Arctic amplified warming, affecting practically most of Siberia, which I've labeled. So we now go to heat waves, and we all know that heat waves have recently increased incredibly, far faster and more severe than had been projected. And on all continents, we've had unprecedented heat waves, temperature increases. This from Working Group 1 shows that. And it shows the importance of heat waves on the biosphere carbon feedbacks and the forest fires in particular. So we can see the quote that from the Working Group 1, that climate change is already affecting every inhabited region across the globe, with human influence contributing to many observed changes in weather and climate extremes. Now, I've mentioned that, and it's so important. This is the IPCC's way of showing the regions, and you can see that practically all the regions of the world have been experiencing, this is since the 1950s, increased frequency of heat waves attributable to climate change. They have another similar map, Working Group 1, on heavy precipitation, and that showed that climate change-driven increased heavy precipitation was happening on all continents, with almost all regions in Europe and Asia affected, almost all. They had one on drought, and there is climate change-driven increased drought on all continents, with most regions in Africa. Africa really severely impacted by drought. This shows an example of the IPCC's observation and their projection on heat waves. And this shows California heat waves, which is quite a dramatic record. It shows the big increase in the frequency, in the duration, and the heat wave intensity. And as the IPCC has reported, there's nothing more definite that all three are going to continue to increase on an accelerating basis. And so we come to climate change-driven forest fires, records of forest fires. Now, actually, it's only quite recently that the science has determined that not only are the forest fires increasing, but that they're driven by climate change. That's quite recent science. Working Group 1 has this dramatic graph of forest fires globally from 1985 to 2015. And you can see the upper one is the wildfires with climate change. And you can see how rapidly that's increasing and accelerating faster than the wildfires without climate change. We have a study, 2019, of biophysical feedback of global forest fires on surface temperature. Forest fires increasing greenhouse gases, increasing surface temperature even more as feedback. This is a very recent paper from Canada. It shows observed increases in extreme fire weather, which is driven by changes in atmospheric humidity and temperature. So you can see that the forest fire weather and the forest fires are high up in the northern latitude, subarctic. And the paper says that these trends are likely to continue as the projections indicate that the changes, the temperature increase, the heat waves will continue to increase. This is the first big land carbon feedback from global surface warming. You're looking at one area of the massive pine beetle kill of the forests in North America. The pine beetles survived the winter, big change, and so they went crazy and killed the forests for the first time, and a big CO2 feedback emission. Drought. We're pretty well aware that we have trouble with drought, and this shows present and also projected drought in this case, and short term at that. This is Working Group 1. It shows soil moisture, and it shows severe, prolonged drought, which is a biosphere CO2 feedback. And as you can see, that the drought increase is widely distributed across the planet. And at 1.5 degrees C, you'll see with the map of crop intensity below in green, you'll see the many major food producing regions that are affected, and even more so, the drought intensity increases with 2 degrees C. The Southwest United States is trending, tipping into a mega drought, and Chile is reportedly in a mega drought. I had to put this one. I just got this the other day. This is the North American Drought Monitor of the end of October this year, 2021. Just look at the severe drought still in the end of October, affecting the Western United States most severely in the Southwest and up into central Canada. And central Canada is having trouble with its crop production because that's where the Canadian breadbasket is. And look at California. Look at poor California in severe drought. And so we come to the biosphere's amplifying feedback sources, the feedbacks from the biosphere, which is being heated up, which feed back more CO2 emissions and more accelerated warming. Now, this is another of my images, and it shows there are multiple and they're enormous biosphere sources of inter-reinforcing, in many cases, amplifying carbon feedback. They're very, very large sources. And all of these sources are operant. They are all emitting more greenhouse gases. In the case of permafrost thawing, it's emitting methane, much more CO2 than ever imagined, and nitrous oxide. This illustration shows this is the coastal Arctic up into the Arctic Ocean, and it shows that the Arctic bioregion holds vast layers of carbon. Permafrost, boreal forest over, permafrost beneath. This shows how huge, how vast the area of Siberian permafrost is. It's the size of Australia. Underneath, you'll see the metric for measuring. We're looking at thousands of kilometers. And this is from Google Earth. And Google Earth shows rather nicely the gray, the vast extents of the permafrost up in Siberia. So we come to the boreal forest. The boreal forest is huge, and it's hugely important to the climate system and to the oceans. It's a circumpolar forest, goes subarctic right around the planet. It's our largest forest, and it holds the most carbon of all the forests. There's that illustration again, and this is just focused on the Arctic and the subarctic. And you can see I've got the boreal forest in green hatched, the wetlands in the brown, and the permafrost in gray. Now, there is a 2021 very recent paper which showed the North American boreal forests are a large carbon source due to wildfires from 1986 up to 2016. The North American boreal forest is being dried by global warming and is burning. On the left, the rapidly increasing frequency of the fires, and on the right, the trend in the increasing burnt area. This is a projection on the Siberian boreal forest. And again, it's published this year, 2021, and it's entitled Climate Change Fire Return Intervals and the Growing Risk of Permanent Forest Loss in the Boreal Forest, the Boreal Eurasia. So you see on the far left, the green, that's the extent of boreal trees. That's the massive boreal forest. And then you'll see the boreal forest fires and projected to 2000, mid-century there, and projected to 2060, by which time most of the boreal forest is burning. Now, we already have big regions of the boreal forest that are burning year round. They don't go out in the wintertime. So this paper says that climate change has driven an increase in the frequency and severity of these fires in the boreal forest, which will get worse. Permafrost is the one I think we all know about, and the one that we have feared about the most. And it's important that as the researchers increase, so have the projections of the rate of permafrost thaw and the emissions from the permafrost thaw. This is very dramatic indeed. This comes from the Copernicus European Satellite Service. On the top there is that range of Siberian permafrost. On the bottom is the CAM's surface emissions of methane. So you see this huge region of Siberian permafrost emitting methane there. It is a huge region. And in the middle is the total column emissions or concentration of methane, showing that this was indeed a large emission of methane. Now, if I had a fire map, if I had a fire map, I could overlay the fire map, and you'd see the intense fires totally overlay the permafrost. Those fires burned through the peatland through into the permafrost. And so, more terrible news from the NOAA Arctic report card, first in 2016, finding that the Arctic had switched from carbon sink to carbon source. Again, something that wasn't supposed to happen until the end of the century. And this happened because it was discovered there was much more CO2 being emitted from the warming, thawing permafrost than anybody anticipated. And there's a good illustration of what happens, how the permafrost emits carbon, CO2, and methane. This is from Working Group 1. This shows permafrost warming from 1980 up to the present. And as you can see, permafrost regions, North America, Alaska, and Canada, very rapid increase in permafrost temperature. Very similar in Siberia, and this is up to the present time. Permafrost holds twice atmospheric carbon. Thawing permafrost is releasing feedback emissions today of methane, carbon dioxide, and nitrous oxide from organic matter from the biosphere, from the land biosphere. It's been known for a long, long time that at some point, internal heat generation by the microbes being brought back to life makes permafrost thaw self-accelerating and irreversible. Now to the Amazon, the one that tragically is very, very well known. The Amazon was a huge carbon warehouse, and it should have been left intact, of course. The science on the Amazon is similar to the other rainforests. Really terrible recent news that deforestation in Brazil's Amazon rainforest has reached the highest level in over 15 years. This shows the image of the Amazon, the original extent of rainforest. There you see Amazon tropical peatlands, quite a large area. On the right, you see the rapid temperature increase of the Amazon region, and you'll see the repeated severe droughts. The Amazon is being switched, at least, from its once huge carbon sink to source. We've had several papers published. This particular one, this year, 2021, shows the Amazon has switched. It's emitting more carbon than it is absorbing. So the oceans. The oceans, of course, are the largest part of the biosphere. They are, in fact, 99% of Earth's habitat, living space. And the oceans are the largest component of the climate system. There are several climate change-driven potential amplifying ocean carbon feedback processes from the ocean. The one that's best known is that warming of the ocean surface water reduces the amount of CO2 being absorbed, and thereby that's a carbon feedback. More CO2 is left up in the atmosphere. The one in bold there is particularly important. Marine heat waves, and they are getting, this is a relatively recent phenomenon, they are getting more severe, and they can impair phytoplankton function. This has been published. The other one right at the bottom is also a terrible, what looks like now probability, and that is affecting climate change, affecting the ocean carbon pump. This is the ultimate sink of carbon of the whole biosphere. And a paper published in 2019 found that different science, which showed that we can be looking at the impairment of this as well, and of course, much more CO2 again being left up in the atmosphere. Now, the worst, very recent news, and it is shocking indeed, is that the ocean and land carbon sinks that we know have been sinking, absorbing about 50% of our industrial age CO2 emissions. They are now becoming less efficient as carbon sinks, long before expected. This wasn't supposed to happen until the end of the century. This is the first time that the Global Carbon Project, the authoritative annual report on CO2, has stated that globally during the last decade, climate change has reduced the land sink by 15% and the ocean sink by 5%. I think this went unnoticed. This is a critical finding. And looking at Working Group 1, their projection, from what I can see there, the land carbon sink can be reversing 2050, mid-century, and the ocean carbon sink can be reversing, much more uncertain, but could be by the end of the century. This we must not enter or go near, 2 degrees C. And we discovered this in the Hothouse Earth paper in 2018. And there are the multiple inter-reinforcing feedbacks of the planet, of the biosphere in particular. And the quote was, "The collective human action is required to steer the Earth system away from this potential catastrophic threshold to stabilize it in a habitable interglacial state." Now, when you look at the supplement of that most important paper, you find the large feedbacks, most of them biosphere, and that every one is triggered at 2 degrees C, every single one. So yeah, we cannot go near 2 degrees C. This is just to point out from that paper that the biggest source of feedbacks in the paper was weakening of the land and ocean sinks. This is from UNEP, their annual most important report. And this is the UNEP GAP report of 2021. It shows current policies going exactly in the opposite direction to what the IPCC and Dr. Lee says have to happen. The current policies in brown, you'll see that in 2020, that was the danger limit. That was the time that for 2 degrees C, as Dr. Lee said, as well as 1.5 degrees C, have to go into rapid decline. This is the Global Carbon Project, the global fossil fuel CO2 emissions from 1990 up to last year. You see that sudden sharp decrease due to the COVID pandemic, but government's financing increased, so it's rebounded almost right up to its record level at 2019. This is important. It's from the IPCC 1.5 degrees C report. That showed back in 2018 that we were going to reach 1.5 C by 2035 from the blue models, projecting models. Now we're looking from the Working Group 1 at the early 2030s or 2030. This shows 2 degrees C projected by 2045. This is no time at all. Safe biosphere boundaries, there's been several published. This is my favorite. It's from Kate Raworth in 2017, but she didn't have ocean, so I had to add in ocean acidification. Our safe boundaries for our future are broken. The IPCC 2020 deadline for 1.5 degrees C and 2 degrees C has been missed and will continue to be missed by the government failure at COP26. There's no improvement from COP26 on the national emissions targets, which put us, according to UNEP, at around 3 degrees C by 2100. Today's biosphere and climate change reality, with the 1.5 degrees C and the 2 degrees C and the multiple biosphere carbon feedbacks and tipping points, I want to point out that this continued delay of measures to put global emissions into immediate rapid decline, as the IPCC has been saying, totally ignores the 2020 deadline, ignores the large sources of many biosphere feedbacks, and ignores today's children and future generations. Okay, so I'm going to wrap it up there.
If you are in the audience and you'd like to put a question in the chat box, the first one, what can we do to get the biosphere into assessment projections and recommendations?
How do we get the biosphere into the assessment projections? Well, this has been very, very slowly sort of increasing in the assessments. It's the IPCC assessments, their projections, their model projections of global surface temperature increase and the projections of the impacts of that global temperature increase do not include these many large source amplifying feedbacks.